Today, we're going to be doing how HLS and SystemC is delivering on its promise of design and verification productivity. I wanted to make sure that you guys knew what we were trying to do with this session is both give you a brief introduction to SystemC and the synthesizable subset, but I want to spend most of the time with our two users, Intel and NVIDIA. So to give you guys a real solid flavor for what we're doing now inside SystemC in production work. So we'll spend most of our time there. And since we don't have the Cadence folks, they were not permitted to come to the conference. So we have a section that talks about the SystemC Accellera standard that we don't have a speaker for. So I apologize in advance for that. Okay? All right, so we'll go ahead and start with Stuart Swan from Mentor, who's an HLS technologist and architect. And he's been doing SystemC for 20 years, a long time. So our technical expert who's recently come working for Mentor in our group here and helping to drive the SystemC architecture that we're working on now. And previously came from Qualcomm, where he was doing a lot of work on the SystemC side.
So thank you, everybody, for coming. Again, my name is Stuart Swan. So this is a very brief introduction. It's probably the most brief introduction to high-level synthesis I've ever seen. My assumption here is that people are familiar with RTL synthesis and maybe a little fuzzy on what HLS actually is and what it can do. In a nutshell, what high-level synthesis does is it takes input, which is either SystemC or C++ models, and a set of synthesis directives, and a technology library spec, which might be something like, oh, I'm using TSMC 7 nanometer, or I'm using Xilinx Stratus, or whatever. And I want to synthesize that into RTL that is going to have good QOR and is going to meet my power, performance, and area targets and so forth. And this is kind of conceptually to what RTL synthesis does, right? RTL synthesis takes RTL in a technology library spec and clocking directives and so forth and generates a gate level netlist. So we're basically just moving this up one level and saying, let's use a more abstract model and basically use that model as an input to the tool along with directives and a technology library spec to generate the RTL, and then use a traditional RTL synthesis flow from there on. What the HLS tool actually does very precisely is it looks at the area and delay of all the operations in the design. So for example, if you're designing a multiply accumulate, it will look at the area of all the adders and all the multipliers and so forth in your technology library, and it will construct the RTL so that you have good power, performance, and area for the implementation. It will also schedule all the operations over the available clock cycles. And one of the differences between high-level synthesis and RTL synthesis is that it can add clock cycles into your design if you allow it to, and it can push operations across clock cycles. It can also do things like, if you have memory accesses, memory reads and writes, it can schedule the memory read and write operations across different clock cycles. These are the activities that typically RTL designers need to do. The high-level synthesis tool, kind of in contrast to an RTL synthesis tool, can optionally increase the latency. And this is beneficial for two major reasons. The first thing is, if you increase the latency within the design, you will increase the opportunities for resource sharing. So if you need to do 2 multiplies, but the latency is 2 clock cycles, you can share a single multiplier in each clock cycle to implement that operation. This reduces the area of the overall design. This also has the ability, by stretching the latency of the number of clock cycles, you can get positive slack at the RTL level. So if you constructed a design where normally you wouldn't meet timing in RTL, this high-level synthesis tool can ensure that you will actually meet timing in RTL. And the last thing that high-level synthesis tool does, it generates RTL that's functionally equivalent to the input SystemC model. In doing this, it automatically creates the control FSM, all the sharing muxes, and pipelining logic and so forth. There's a couple key things that the synthesis tools typically do. Some of the most important things are on loop transformations. Basically, if you have a very simple design here, which is a multiply accumulate of 4 input numbers, where we take 4 input samples and 4 coefficients, and we do a multiply and then an accumulate operation across those 4. In RTL, you can implement this for optimal area by using a single multiplier and a single adder, and you can basically sequentially implement this operation over 4 clock cycles with a design like this. Alternatively, you can unroll this loop and implement it in parallel with 4 individual multipliers and then 3 adders and then pipeline logic. And what the high-level synthesis tool does is it can automatically do this for you based upon the input directives that you hand to the synthesis tool. And you can actually do this type of exploration. You can do partial loop unrolling, and you can change the pipelining characteristics so that you can meet specific throughput targets for your implementation. And these types of transformations are quite tedious and take a long time to do in RTL, but they're quite fast to do in high-level synthesis tools. The next thing that it does is that based on your target technology, it will schedule operations across those clock cycles and allocate basically the most efficient resources to implement all the functionality that needs to be implemented in your design. And then lastly, what it does is register and resource sharing. So it will automatically look at the lifetime of data and when various operators are needed, and it will share those resources across clock cycles and minimize the register cost so that you have a smaller design. When the user is using the tool, he basically needs some way to know how the tool is scheduling his operations across clock cycles so that he can optimize, so he can understand basically what the tool is doing. So just as if an algorithm designer was telling an RTL designer to go design some logic, the algorithm designer and the RTL designer need to agree on a structure and understand how these operations are going to be scheduled. For example, when memory reads are going to be scheduled memory writes. So that in this case, what the tool can do is graphically show you these operations across a schedule view, and can also show you things like data dependencies. And this can help the designer understand where there are bottlenecks in his design and how he may want to recode his design to get better results. One important capability here is the need to be able to cross-probe back to the source. So that in the tool, you can click on something within the graphical view and see the source code. Data dependencies are the green lines here, the curvy lines. And these small boxes here are the operations that I was discussing. And the bigger red boxes here show the mobility of these operations across the different clock cycles that the high-level synthesis tool is allocating. Conceptually, what an RTL designer would do is he would probably build a mental model of this in his head. But in this case, the tool automatically shows him where he can schedule operations or where these operations could be scheduled. It also shows him things like which loops are taking most time in the design. So the idea here is that the designer can get a very good idea of what the flexibility is in the design and where the costs are going to be. So one key thing, and this is actually the thing I think that trips up most companies that are adopting high-level synthesis in most groups, is that to get good quality of results, or QOR, you need to properly capture the hardware architecture when you write your code. So you can't just take any arbitrary C code and throw it at the tool and expect to get good results. And in particular, you need to code in such a way that you reflect the hardware architecture in your code. So you need to reflect the proper input-output structure and the proper memory architecture. You need to code the proper process structure. So hardware is concurrent, software in general is sequential. And with a language like SystemC, we can explicitly express concurrency using things like SC threads, and we can express the concurrency in the design that we're going to want to have generated in the RTL, in the hardware. So it's very useful, I'd say, that when people are using high-level synthesis tools, they should have a rough idea in their head of what RTL will be generated and how expensive it will be. For example, anybody using a high-level synthesis tool needs to know, for example, that multiply operations are expensive, and a 32-bit multiply operation is much more expensive than an 8-bit multiply operation. And you need to code your design up front with these considerations in mind. But you don't need to code your design all the way down to the level of Verilog RTL. So there's a lot of details, for example, the register sharing, the construction of the overall control of a particular block that you can leave to the tool, and it can take care of details like loop pipelining and so forth, memory access scheduling and so forth. So this is an example of a typical HLS flow where the user codes in SystemC or C++ and does most of the verification and refinement and debugging at this level. And typically, the test bench environments used at this level will be SystemC test benches, MATLAB, or System Verilog UVM. And you can do C code and functional coverage closure here on the SystemC model. And this pays off because basically all the work that you do to do verification and code and functional coverage closure up here sort of transfers to the RTL that gets generated later. The next thing you do is you run the high-level synthesis tool, and via these synthesis directives that I described earlier, you can explore and refine the architecture. For example, you can change loop unrolling directives, you can change pipeline initiation intervals, and so forth. And once you're satisfied with the QOR, you have generated RTL Verilog. And at this point, the verification flow looks very similar to a traditional RTL verification flow, but it's typically much quicker because you can basically use the same verification environment, including System Verilog EVM, to basically repeat your functional coverage closure and the RTL code coverage closure at the RTL level. After that point, it just becomes a traditional RTL synthesis place and route flow using traditional RTL synthesis tools. So to sum it up, why is high-level synthesis beneficial? The first thing is that the model is at a higher abstraction level, and this means that it's smaller and there's less opportunity to make mistakes. The next thing is that the model is more easily reusable, and this is because it's much more feasible to do parameterized design in C++ than it is in a language like Verilog. For example, you can use template parameters, and you can use higher abstraction data types such as fixed point types and so forth within a C++ or SystemC model, and it's virtually impossible to do that in an RTL model like with a language like Verilog. And the last thing is that it's much easier to retarget to different silicon technologies. And one of the reasons why it's easier to retarget is that when you go from a big jump in a silicon technology, the delay characteristics of various operations, including things like memory I/O, memory reads, and so forth, can significantly change, and those can impact the best architecture for a particular target technology. And what the high-level synthesis tool is able to do is sort of look at the target technology that you're moving to and do minor re-architecting to optimally retarget to your newer technology. The next thing I mentioned is that verification is faster and easier, which I explained in the previous slide. And really with high-level synthesis, you can easily and quickly explore power and performance trade-offs that's really not feasible to do in RTL design because it's just too expensive. And the last thing I'll say is that our experience, and I think that most companies that have adopted this, is that the quality of results that you can get with high-level synthesis is very competitive to handwritten RTL.
I would like to introduce to you Matthew Bones. So Matthew's been a design verification methodology expert at Intel, working on SystemC and HLS for, the last 9 years or so. Here to talk about really his user-based experience and give you a little idea of what he's seen in real projects using HLS at Intel.
Today I'm going to focus a bit on how at Intel we get the best optimizations for power and performance using HLS. I'll also mention some of the other benefits we see along the way. At Intel, and I think elsewhere in the industry, people are seeing a lot of growth of HLS in many different design domains. This is due to powerful tools and some of the other aspects of the design methodology that let you accelerate your design and verification phases. I will claim there's benefits for data path and control-dominated designs. Traditionally, people are using HLS more for data path, algorithmic specific designs. But we're seeing that extend a lot more into things like cache controllers, memory subsystems, areas that HLS hasn't traditionally been used for. In the past few years, we've seen a lot more there too. The benefits I'll talk about are roughly your schedule, how you get best power performance, and opportunities for improving your software quality or firmware quality. So I picked a few case studies. My background is I work in a central CAD support and methodology team, so I've had the opportunity to support a lot of different teams at Intel on a lot of different types of designs, and on occasion even code some of those design elements, go on loan for a quarter or so. So I picked a few case studies that I've seen out there. They're really quick just to give you an idea of the flavor of some of the benefits we get. The challenge, I think everyone knows this, sees this. We're doing very big, complex designs. Finishing the design itself can be a lot of work. And so often exploring for best power and performance can fall by the wayside. Also, I would say in general, most designs say power is their most important metric. This can vary depending on what you're doing, but quick and short, power is number one. This could be data center costs. This could be, mobile devices. You have your phone on battery. You're concerned about power. I actually read an interesting statistic that, the majority of website access is now done on mobile devices. This can vary depending on the type of site. I think news was 60%, banking's like 70%. There's one industry that's about 90% for mobile devices, but that's over in the adult area. I won't get any more into that. And, we're getting by with traditional RTL design methodology, but some of the big issues I see are your power performance estimates are available pretty late in the design phase. What do you do with that? It's also often high effort to make any changes to address those and improve things. And the language we use improves a lot. I like System Verilog. I think it has some great verification features. But overall, it's the same abstraction as 30, 35 years ago, meaning you code what's between two registers. So I'm going to talk about here what I think works a little better for most or all type of designs. Some of this will rehash a little bit what Stuart went over, but I'll try to give my take on it. So as mentioned, this is from a SystemC source. If you haven't heard yet, SystemC is just a library on C++. If you know C++ and some hardware constructs, you know the basics. You're trying to describe the functionality of your design and leave the tool and some directives to do many of the details for you. So parallelism, throughput, latency, some of those type of things. Like Stuart mentioned, as this tool runs, it characterizes all the parts of your design, multipliers, adders. To put out a good schedule, timing clean, you need to know that information. Okay, so this is similar to what you saw before. What I'm trying to show is there's the SystemC model, your technology library, and sandwiched in between is the HLS directives and any code parameters. You can write highly parameterizable code, and some of the ways we realize that are going to an ASIC product, next generation of your technology node, and FPGA. As well as you can scale in other ways. You might have a very big design you're sending to the server space, or you might have a very scaled down version you send over in the mobile space. So I'll tell you what I think the top three benefits are that I see. Roughly faster time to market or, shorter time to silicon is one of the big ones, and maybe the biggest depending on who you talk to. Some of the designer benefits, you do more with less code. The directives for the HLS tool let you change quite a bit without changing your source code. I'll get a bit more into that. And even effort savings in tracking spec changes. So I often see a world where the spec's changing very late in the game. Sometimes making those changes in RTL is a bit of effort. On the verification side, we tend to see that can start a lot sooner. Getting the SystemC model to the level of functionality where you can begin testing often happens very early. Getting the RTL up and healthy enough for testing may be fairly late. The other thing I want to mention is getting this done early leaves you more time for tuning, optimization, whatever you like to call there. And another area you can save time is on the physical design of this. The HLS tool is meant to generate RTL that is timing clean. This means the RTL you hand off to the back-end team should go through synthesis. You can leave guard bands for routing. And in general, people are happy with the RTL they get when you pass it on to the next in line. Number two, this is probably my favorite individually, in my opinion, is I like that we can achieve better power and performance. This is primarily through exploration. You could do some of these techniques with RTL, but it may take you years. You can't iterate as quickly, and often there's not the time to get there with the complexity of the designs. So making quick changes in the design you can do with pretty low effort. I like that we get earlier power estimates. As soon as you can push the button to get RTL from your SystemC, you get some area power estimate. And if it's not good enough, you go off and do the optimization and tuning. And as mentioned before, you get custom RTL that targets your specific process node and should meet timing, look good, all the good QOR type characteristics. The third reason that I don't always see with design teams, but it's becoming a bit more popular, is to reuse a lot of this code in other contexts. So you'll see many virtual prototypes out there are done using SystemC. Getting a common language here for your design source as well can give you opportunities to reuse that in the VP space. So you can test your firmware because this runs much faster than RTL. It varies a lot on your design, what type it is, but in general, you're about 100 times faster than RTL. I will mention there's kind of two styles of reuse we've seen. On occasion, the HLS source is fast enough as is. This has some pin level details, but just because it runs a lot faster than RTL, it's often fast enough depending on what you need. Now, if you want a true virtual platform where you're trying to boot Windows, you're probably not going to get the speed you need, and that's where we have our second alternative here, which is you have a virtual prototype, have TLM type interface, but you share this common C++ kernel. So more and more we're seeing reuse of the HLS code across other areas. So when I talk about exploring power and performance, the official phrase I'll probably use is design space exploration, but later on when you're trying to save 10-20% power, I might just use the word tuning. I sometimes switch between those. As mentioned, because the directives choose many details of your RTL or implement many details, you can change just the directives and get differences. So I usually say, this isn't always true, but I roughly group it as if it's a tool directive, that's more of a microarchitectural change. So your throughput and latency, memory accesses, things like that are the big ones. But I will say, some exploration does require edits to the SystemC source. So if you're trying to change the partitioning of your design or the ordering that things happen in, often the tool can't do that for you, but you do have to change the description. I will say that's less effort than RTL. I'll get a bit more into the pictures later, but what this is roughly saying is we can change our throughput with a tool directive, and we can change our memory access pattern from doing an SRAM, where you have a single read-write port, a register file where you can do reads and writes concurrently, and even some dual port or just flip-flops here where you can get very concurrent parallel accesses to your storage. I'll talk a bit about pipelining here. Stuart had a very similar picture because this is very common in many designs. Your multiply accumulate here. This is specifically from a FIR filter example in the signal processing space, but you look in deep neural nets elsewhere, you will see the multiply and accumulate all over the place. So let's start with what a designer might do when trying to code RTL for this. He hasn't seen the light for HLS yet, let's say. Often a designer has a rough idea of what's the cost of a multiplier, an adder, timing-wise. So what the designer might here do is say, well, someone told me the multiplier and the adders are fast enough. I'll just do all these in one clock cycle. And here, clearly, it doesn't meet timing. There's too much there. The designer might say, okay, I need a little more time. Let's push out one of my ops into the second clock cycle. Oh, we still have a little issue here. It could meet timing, but I'd rather have a more robust design. And then they might go further and say, well, let's spread them out as much as possible. This is great for your timing, but you may have more stages than you need. You're wasting flip-flops, essentially. You could go back and think further, and what the last bit I have here is what I'm calling the well-balanced pipeline. So this is really none of my ops have real timing issues. No one's creeping up into the next clock cycle. This type of well-balanced pipeline will definitely meet timing. So I mentioned a case study. I think I only have one slide on this. But this is a specific case where we had, in the signal processing space, I don't know if you're familiar, MMSE is an algorithm you'll find. So in a 5G modem space is where this came out of. What we see with nearly any type of design where you can change the latency, where you don't definitely need 3 clocks latency, where you have some flexibility here, is over and over again you'll see a curve similar to this. So if your latency gets too low, you can't meet timing. You're squishing too much into these clock cycles. And then if your latency gets too long, well, things look pretty good, but you're wasting registers over here potentially. So often there's a sweet spot in the middle, and this U shape is quite common. What I have here is some data from, I think this is 6 or 7 separate HLS runs, where the tool is given a different latency directive. Say one run's give me something between 60, 65, the next is 65 and 70. And here's what we got here. These are about a 30-minute HLS tool run, so in a half day you can create a graph, something like this. Often the HLS tool will do a good job at finding the best case, but we've also learned some better techniques to perhaps improve on that a bit or give the tool more hints or direction. So some data from that last case. I should mention early on this started as a case where there was an existing RTL design, and as part of the evaluation of using HLS, the idea was code this up in C++ and compare how it looked against the existing RTL. This is one of the more extreme cases I've seen in savings. So I don't know if this is always the norm, but pretty impressive. What happened here is the HLS design ended up being 34% smaller on area, and this correlated roughly to dynamic power savings. And this is mostly due to the multiplier sharing and scheduling that HLS can do for you. So often an RTL designer may miss these sharing opportunities, or they can find them, but it's quite a bit of effort that they might like to spend elsewhere on functional correctness. The tool also gave a better latency here, almost 30% savings on the time to get through the design. This is primarily because the existing RTL was developed on a tech node that was 2 generations previous. You take that to a newer tech node, theoretically you should have more room to work with, you should get a lower latency. So there's often these RTL designs that may have become stale or good enough. People often think they're leaving 5-10% performance on the table, but there can be pretty extreme cases here if you have an old design. The other option that was interesting here is we could play with the throughput. So initially this design only had to get 1 input every 4 clocks. It eventually needed to go 4x faster, and quickly with HLS we can say, okay, I'd like a design pipeline with the initiation interval of 1. So this means a new input every cycle. This is equivalent to the old design, and we can find very interesting trade-offs, such as I can get 4x the throughput for only 2x the area. You can also play games with clock frequency. You could say, well, I want to get the same throughput at a lower clock rate. It's a little bit more area, but on dynamic power, this was a huge savings. So there's really a lot of opportunities here with algorithmic designs to just push the button and get a variety of designs with very little direction for the tool. The other case study I'll talk about is less in the algorithmic space. This is a high-frequency memory fabric, call it a crossbar router, whatever you like. This is mostly control logic, FIFOs, things like that. So this isn't one of the designs I can just ask the tool to pipeline and it says somewhere between 5 and 7 cycles. Often you want to say more exactly what you want here in these type of designs. But we still see some benefits with HLS. This team initially, some of the challenges they saw is that they didn't really get timing analysis until very late, until really the whole design's put together. You need all the pieces, the arbiters, FIFOs, all that in place. And this was really high effort to analyze what was happening and then making change. Okay, good luck. That's going to be a whole new set of effort there. When you're using the HLS tool, what's nice is because it has the technology library, as it goes along, it will be characterizing the operations in your code or even regions of your code. You can have it characterized for timing and area. Let me show what this means a bit more. In this case of the fabric, the arbitration So just to be clear what the fabric is, when I show like a 4x3, this is saying I have 4 requesters talking to 3 memory targets. And what really limits the max frequency of this tends to be how many agents you have to arbitrate between. So very quickly, we can give this type of sequential code. This is one benefit is this is just procedural code, write it how you like in C++. And at the end of this, you should have chosen who wins your arbitration. Now, in the RTL design, this might be spread across multiple arbitration modules. It's a bit more piecewise how you get the timing there. In this case, I can just say, well, what's the delay through this region of code? I can call this my arbitration region. And then as the tool runs, I can say, well, what if my number of masters is 4, 5, 6? I can get the delay for this bit of arbitration code here. Even further, though, the tool can just tell me, am I meeting timing? So putting the arbitration aside, does my whole design meet timing? So we can get things like, oh, I have 4 masters here. That easily meets timing. Go to 5, it's a little iffy. I go to 6, it's not going to meet timing. And if I don't meet timing, I might need to think a little harder. Do I want to actually change the arbitration algorithm? Do I need a multi-level fabric? So really, you can get this data early so you have time to make changes or think what you want to do next. The last case study I've taken here gets into the nitty-gritty of digital design a bit, so I apologize for anyone that are more pros in verification, system-level design. This is getting down in some details, but it's pretty interesting. So we talked about dynamic power. I think people have a pretty good feel that usually there's a rough correlation to your area and how active your chip is. Often how leakage power is managed, so that's the power your device is always drawing when it's on. Often how that's managed is by having some cells. So in your technology library, you'll have cells that are just your average cells, kind of slow cells, but they'll have very, very low leakage. And then you have alternatives called low VT, LVT, or ULVT, ultra low. These are your faster cells, but you pay for it with quite a bit more leakage. So the leakage goes up very quickly as you begin to use these faster cells. Most designs use a mix of these two, so you try to, in general, use many standard cells. You use fast cells where you need to fix up your timing, so often there's some mix here. Rough idea, if you're a server, you might be tolerant of higher leakage. Often you will be able to power down certain power planes when you're idle. You have more tricks to play. If you're mobile, though, you often are always listening or always on, depending on the function of the chip. And when this is the case, you can't really save that leakage power by powering down. You need to be ready to go. So when it comes to a mobile design, we're really looking to minimize any of these high leakage cells. Now, how do you do that with HLS? It's similar to what I showed before with active power. Really, what you're trying to do is have a well-balanced pipeline. But even further, you're really considering what you're leaving here as a guard band. How much extra time do you want to leave for any unpredicted delays, routing delays, all that other stuff that happens after the RTL? So what we usually do is leave, a reasonable guard band here. This means most of your operations use slow cells, and if it gets a little tight, some LVT cells sneak in. If low leakage is the primary goal, we keep a larger guard band here. So what this means is if routing, anything here adds some unpredicted delays, well, we left lots of room for that. We shouldn't have to go to the LVT cells from that point. So the case study here I have is similar to the first one, a different block I won't go into, but in the 5G space, your transceiver needs to nearly always be listening to the radio waves. And like I mentioned, low leakage will be important so you don't take a hit on battery life. This is a specific case where to meet the leakage goals, they really needed to do 90% of the design with these very low leakage cells. This design was made up of a couple portions. Most of the signal processing algorithmic content here was done with HLS, and there were some areas, legacy code, embedded cores here that were done with RTL. What turned out in this specific case is that the handwritten RTL needed these high leakage cells to meet timing, and they were using more than budgeted. What was nice here is we could repipeline all 20 blocks in this transceiver chain, give them that large guard band like I mentioned before. And now the HLS portion of the design isn't using any of the high leakage cells. We still complain about what these guys are doing, but overall the chip met its budget. Stuart mentioned this a little. When you change technology nodes, you're giving the tool the tech library. And so what this can do is make use of potentially those lower delays you have. So here's that U-shaped curve I mentioned before. And if you think about it, a new process technology library tends to be faster. The delays will be shorter. So this curve basically will shift left. It'll shift down to one area, but as far as delay, it will be shifting left. So if you had a sweet spot here, your U curve shifts left, you now have a less efficient design unless you're rerunning to get your new design over here. And also the parameterization you can do with HLS, with SystemC and C++ specifically, goes a bit beyond what you can do with Verilog. One example might be you could have the same filter code in signal processing and have that with a bunch of different latencies, throughputs, different varieties, depending on where you are in your filter chain and what you need. And yeah, like I mentioned, we can reuse the same SystemC IP across the spectrum from server on down to mobile. So to wrap it up, HLS finds low power and efficient solutions. I believe in the algorithmic data path space, it will beat handwritten RTL by 99% of designers. In the control-dominated space, you have to be a little more careful of your coding. You need to learn a bit more, but you can also get gains here in time to market and perhaps area. SystemC gets us usually less code. This also varies depending on the type of design, but I usually say it's about 3 to 10x less than what you're doing in RTL as far as lines of code. You simulate 100x or more faster, and also just being in the C++ language, you'll find there's opportunities for reuse, whether it's a VP domain, a reference model for verifying RTL, different uses there. So the C++ language is a good common place to be for other modeling tasks. So I've told you all the nice stuff now. The one thing I have to say is, for us to get to the point we've gotten at Intel, it's taken a fair investment. Not only, people think of the new language as the first thing. I got to learn a new language. But even further, you have to learn a different style, a new design methodology. Now, it's possible in SystemC to effectively write RTL, but you're not really reaping the benefits. So beyond just switching languages, there's also the methodology question. It comes up now, okay, I'm using SystemC C++. Do I do my coverage in that language? What's my IDE or GUI I like to develop in? That answer might be different when you go from Verilog to SystemC C++. So overall, I want to say, there's an investment, there's a learning curve, but the end place we've gotten has been pretty satisfying when you can see significant power savings and speed up, whether people say I get to market faster or I did the same with half the people. Overall, it's been a win for both the schedule and the power performance areas.
Next up, we have Ranga Venkatesan from NVIDIA Corporation. So Ranga is a senior research scientist at NVIDIA, graduated from Purdue with his PhD. So Dr. Venkatesan specializes in machine learning. That's what I've been working with him on for a long time. So machine learning accelerators, memory architectures. So here to introduce what they have been working on in the last 5 years, working with SystemC and HLS.
Thanks for the introduction, and it's my pleasure to share some of the work that we have been doing in the high-level synthesis space. So the title for this talk is MatchLib-based object-oriented high-level synthesis-based methodology. So this is the brief agenda for this talk. I'll briefly start from the motivation, describing the chip design complexity, and then I will talk about our object-oriented high-level synthesis approach. There are 4 key aspects that I would like to cover: our C++ and SystemC to layout flow, and I'll talk briefly about our MatchLib open source high-level synthesis library. And then I will talk about latency-sensitive channel approach and why it is very critical in a high-level synthesis-based design methodology. And then I'll talk about the verification flow that we have. And then I'll briefly talk about the few test chip demonstrations that we did to validate this flow and go in depth about our recent accelerator called RC18. It is a scalable deep learning accelerator, which is targeted towards very high efficiency of about 128 TOPS and approximately 10 TOPS per watt energy efficiency. And this was done from spec to tape out in 6 months with less than 10 researchers, and I'll share more details on that. So the primary goal for considering a high-level synthesis-based approach is the continuous increase in chip design complexity. If we take that example of NVIDIA's Xavier SoC that was announced in 2018, it has about 9 billion transistors, and it has an 8-core processor, a GPU, and several accelerators for vision, video processing, deep learning, etc. It was arguably one of the most complex SoCs in 2018, and it took about 8,000 engineering years to design it. Now, if we consider the next generation, NVIDIA Orin, which was announced last year, it has about 17 billion transistors, and it is targeted to achieve about 7x the performance of the Xavier SoC. So as a result, what we see is that the demand for more capabilities and has been going on the rise, and we try to integrate more and more transistors to enable this. For a long time, for several decades, we have been having a free lunch with the help of Moore's law. We are able to integrate larger and larger transistors every generation at fixed power and as well as cost. However, at the beginning of early 2000, we actually saw the end of Dennard scaling. As a result, we were no longer able to scale more transistors in a single chip at fixed power. And more recently, we also are seeing the end of Moore's law with diminishing ability to scale at a fixed cost. However, the demand from the customers are continuing to increase, and there is an ever-increasing need for design innovations and automation tools to deliver more transistors and higher capabilities every generation. And as a result, we explore a methodology where we can lower the design cost and integrate larger number of features and enable faster time to market. So if we look at a typical product design cycle at NVIDIA, it takes approximately 3 to 5 years for a new feature to be added from the R&D to the product phase. A significant fraction of this design time, about 70%, comes from RTL design and verification effort, and this decides which features eventually make it into the final product. So we started a research project where we targeted about 10x reduction in design and verification effort. The key idea was to overlap the architecture and implementations to enable faster time to market and have more features in every product. There are two key aspects to our high productivity design approach. The first is to raise the design level of abstraction for the hardware. We use the high-level languages like C++ and SystemC instead of Verilog, and used automation tools based on high-level synthesis to generate the RTL. We heavily relied on reuse and developed libraries and generators. We developed a library called MatchLib, which is basically a collection of commonly used microarchitectural components, which I will describe in more detail in the following slide. The second aspect is agile VLSI design process. Here, small teams jointly work on the different phases of the project, architecture, implementation, and VLSI simultaneously, and use automation tools for continuous integration. And we used agile project management techniques to enable 24-hour sprints from SystemC to all the way to layout, and this enabled fast iterative feedback continuously throughout the project. The front-end design methodology we call object-oriented high-level synthesis. It is a push-button flow from SystemC to layout. We code the architectural models in Synthesizable C++ and SystemC, and leverage high-level synthesis tools for generating the RTL. A key aspect of this is the heavy use of object-oriented high-level language features and the use of libraries to reduce the design effort. Our library is called MatchLib. It stands for Modular Approach to Circuits and Hardware Library. You can imagine this as like an STL or Boost that we have in the software domain, but this is designed for the hardware design process. It has a number of microarchitectural components that we use commonly in the design process, like crossbars, routers, arbiters, etc. And all these designs are highly parameterized. They are pre-verified and optimized for QOR. In the earlier talk, there was a mention about the importance of coding style, and we try to capture most of the good coding styles in the creation of this MatchLib in order to make it easier for the designers to use these MatchLib as Lego blocks in building the hardware models. And we have also open sourced this library on GitHub, and we welcome people to try it out and welcome feedback and contributions for MatchLib. The other key aspect of high-level synthesis-based methodology is that the latency or the schedule of the pipelining is determined during the high-level synthesis process and is not available at the design time. As a result, it is important to decouple the design of different blocks and their timing dependencies during the design process. For this, we used a latency-insensitive channel-based approach, which enabled modularity by decoupling the computation and communication in the architectures. Our latency-insensitive channel library is called Connections. It is part of MatchLib. It has a number of different options to choose the appropriate choice of channels during the high-level synthesis process. It offers a similar API that is channel agnostic, so that the producer and the consumer blocks can be designed independent of the choice of the channels. Further, the producer and the consumer designs are also completely decoupled, and therefore they can be targeted for arbitrary pipelining and scheduling in the design process. The channels will be automatically mapped to ready-valued interfaces while synthesizing the RTL. It can be a combinational channel or a buffered channel depending upon the use case. In the extreme case, we can also think of introducing a full-fledged on-chip network between the producer and consumer depending upon the scale of the design. In order to verify the design, we have our test benches also in SystemC. A key difference here is that we perform both the functional and performance verification natively using C++ simulations. There are few major advantages to this approach. First, as mentioned before, we achieve about 50x speedup while doing C++ and SystemC simulations over RTL. As a result, we have faster debug cycles and quick turnaround times. And we also developed a methodology to back annotate the latency and throughput that we see at the RTL level after the high-level synthesis process back at the SystemC level in the connections library. As a result, we are able to do the performance validation, and we see only a small percentage of error during this process. Another key source of verification benefits comes from the use of pre-verified libraries. As a result, we have fewer bugs introduced in the code, and since we are using high-level language features, designers tend to write fewer lines of code, and also that makes it easy to debug the bugs during the verification process. Our verification process is pretty standard. We use constrained random number generators, checkers, line and expression coverage, and assertions, etc. But all of this is primarily done in SystemC. And an ideal approach to verify the generated RTL would be like a formal verification check. However, we have limited tool support for verification check between SystemC and RTL, and therefore we decided to reuse the SystemC test benches for verifying the generated RTL as well. And I would like to mention that a major challenge today in the widespread adoption is lack of formal verification support. There are limited tools available that can do C++ to RTL formal verification. However, a full-fledged system level tool for SystemC to RTL is still a work in progress and is open for research. As a result, we performed all the RTL verification both at the unit level and chip level by reusing the SystemC test benches, and this enabled us to reduce the design effort in the verification time. Our backend methodology was pretty straightforward. We have automatic RAM mapping in the generated RTL and then use standard synthesis and place and route tools to generate the netlist. Another key aspect of this object-oriented high-level synthesis approach, which differs significantly from the earlier approaches, is that typically we have small units and feed-forward paths that were targeted for high-level synthesis. In our project, we are targeting the design of an entire chip using a high-level synthesis-based methodology. The second aspect is an agile VLSI design technique, which enabled us to have like daily SystemC to layout spins. This offered a key benefit is that it enabled fast iterative feedback at different levels of fidelity at the RTL level, at the post-synthesis as well as place and route level throughout the design process. And we enabled this by using small partitions for fast place and route iterations. And in this agile incremental approach, all the RTL bugs, performance, and VLSI constraints kind of converge together towards the end of the process. And therefore, all of these things are optimized simultaneously. And this is in contrast to the traditional waterfall-based model where we have a strong architecture freeze followed by an RTL freeze and then the place and route. Here, all the three levels of abstraction kind of converge together. And this also ensured that we can make better design space exploration and optimize the design for better QOR. Another fun fact is that in the RC18 chip that I will be describing later, we were able to kind of verify the design and fix bugs even just a day before the actual tape-out process. So we had multiple chip demonstrations using this methodology. The first one was called RC17. It's a programmable machine learning accelerator, and it was used to demonstrate that this methodology can be used to tape out an entire chip. We then worked on RC18 test chip. It is optimized for scalability as well as energy efficiency, and we demonstrated that we can simultaneously achieve lower design effort as well as high efficiency using this methodology. In addition, we also had another chip tape out to demonstrate that this methodology can be used to port across technologies, and we ported our RC17 test chip from TSMC 16nm foundry to Global Foundry 14nm foundry and showed that it can be done at low design effort. So in the rest of the talk, I will be doing a deep dive into our latest test chip called RC18. There are two major goals for this project. One was to demonstrate state-of-the-art, scalable, high-performance deep learning inference accelerator. Our goal was to achieve more than 100 TOPS of performance at very high energy efficiency of about 10 TOPS per watt. And at the same time, we want to demonstrate that this is possible with a small team in a high productive VLSI design flow. So this figure on the right shows the high-level overview of the RC18 accelerator. It is a tiled architecture with distributed memories. In order to achieve scalability, we embraced multi-chip modules. Each package had 36 chips integrated and connected together using ground reference signaling based interchip communication. We would like to note that while we choose an organic substrate at the package level, the methodology is agnostic to any choice of packaging as well as signaling approaches. And each chip had about 16 processing elements and had a global buffer that acts like a second level storage. It also integrated a RISC-V controller, and then all these components are connected in a network on chip topology. In order to connect the different chips together, each chip had a network on package router as well as GPIO interfaces for input and output. The figure here shows the microarchitecture of each processing elements. We have a weight buffer, an input buffer, and an array of vector MAC units, and then we have an accumulation buffer to accumulate the partial sums, and then a post-processing unit. A key factor to achieving high energy efficiency was to efficiently reuse the data. Here the data that is read from the input buffer is broadcasted to all the vector MAC lanes, thereby achieving input reuse. The dot product vector MAC units themselves perform a partial sum reuse by accumulating all the partial sum values in the vector dot product before storing them into the accumulation buffer. In order to achieve weight reuse, we adapted a weight stationary data flow where we read one weight and store it in a register, and then read multiple inputs and perform dot product with the same weight vector and write it into the accumulation buffer. In order to achieve scalability, we enabled partial sum reduction both temporarily within the PE as well as across the PEs, and therefore the partial sum values from the accumulation buffer can be received or sent to the neighboring PEs using the routers. Once we perform all the required partial sum accumulations, we use the post-processing units to perform the truncation and other post-processing operations and store the data finally back into the global buffer or the global PE. This design used a number of MatchLib components, and we were able to make fast iterations, ensure that this is designed at a much lower design effort. A key characteristic of this RC18 test chip is the integration at both the chip level as well as the package level, and therefore realize that we have a hierarchical communication architecture consisting of a network on package as well as a network on chip. At the network on chip, we have a 4x5 mesh topology with 16 PEs, one global PE and one RISC-V process connecting together. We used cut-through routing with multicast support, and each router achieved 10 nanosecond per hop and 70 gigabits per link at 0.72 volts. At the package level, we have a 6x6 mesh topology to connect the 36 chips in the package, and each chip had a single NOP router with 4 interface ports that connect to the NOC within the chip level and 4 remote ports that connect to the neighboring chips. Each NOP router achieved about 20 nanoseconds per op and had about 100 gigabits per link of bandwidth, which is primarily determined by the physical layer of ground reference signaling. Another key aspect here is that both the network on chip and network on package were realized using the same router code from the MatchLib, simply by customizing the number of ports and the bit widths to suit the bandwidth demands and latency of the specification. Here I would like to summarize the key methodologies that enabled us to reduce the design effort in RC18. First, we raised the design level of abstraction from low-level Verilog or VHDL to C++ and SystemC. We had a significant reuse in the design process by using MatchLib. We automatically generated the RTL from high-level synthesis tool and also used some of the IPs that are available from the market to integrate them in a single chip. And our choice of tile-based architecture ensured that there is modularity in the architecture level. And we decoupled the compute and communication using our LI channels. Our LI channels also enabled that we have a clear abstraction between the IP blocks and the high-level synthesis blocks and communicate through a standard latency and still channel protocol. We had an agile VLSI design methodology which enabled continuous integration and feedback throughout the design process and enabled daily C++ to layout runs. We achieved scalability by integrating multiple chips using multi-chip module technology. To illustrate the reuse and modularity in the design process further, here I present the processing element implementation. At the high level, we have the PE partition, which consists of multiple different subunits that perform different functionalities. Each of those subunits has a hierarchy of a number of other components that actually perform other sub-functionalities. We have also embraced different coding styles from C++ function, C++ class, and SystemC module to realize this design. The simple feed-forward modules like the data path and the post-processing units are implemented as C++ functions. Modules that have state, for example, the input activation buffer, the wait buffer, and the accumulation buffer were realized as a C++ class. And units and modules that have control logic are realized as SystemC modules. We also leveraged the high-level language features to develop custom C++ libraries like the address generators and the buffer managers. They were used extensively to design the different buffers that were used in the design. The bottom of the stack here is made up of the components from the MatchLib modules, which were integrated in the design of various blocks in the system. So here I present the fabricated MCM-based accelerator. It was a research prototype with 36 chips in the package at TSMC 16nm technology. Each chip was about 2.5 mm by 2.4 mm, integrating 16 processing elements, a global PE, RISC-V processor. At the bottom, we have all the GRS macros, which are analog building blocks, and we have a GPIO for input and output. It had high-speed interconnect links, which achieved about 100 gigabits per second per link. The compute tiles used in the system were highly efficient, achieving about 128 TOPS and 10 TOPS per watt. It also had a wide operating range from 0.52 volts to 1.1 volts and had a frequency range of 0.48 gigahertz to about 1.8 gigahertz. And all this was completed from spec to tape out in less than 6 months with 10 researchers. To summarize, we presented a MatchLib-based object-oriented high-level synthesis methodology, ensured that we achieve significant reduction in design effort by raising the levels of abstraction and using automation tools in the design process. Our object-oriented high-level synthesis flow, consisting of latency-sensitive channel-based abstraction and MatchLib, ensured that we can have significant reuse and modularity in the design process. This can potentially enable faster time to market and have more features in each SoC. For the test case of the RC18 deep learning inference accelerator, we achieved about 10x reduction in ASIC design efforts. I would also like to acknowledge all the people who have helped in this project. This project was sponsored by DARPA under the CRAFT program, and it was a joint effort of a number of different NVIDIA collaborators and collaborators from Harvard and former NVIDIA interns and postdocs. We would also like to thank the support of Mentor Graphics, Catapult High-Level Synthesis team throughout the project.